So, welcome to another session of control system, and as I promised, the next thing that we are going to look at is the response of a second order underdamped system to a unit step input, and that is now what we have, what is there on the board. And you'll find that the unit step input, the reason why we usually make reference to it is that it is the most useful and the convenient input for the study of transient performance. And a typical response is what we have here, whereby we have that. So this is now the step, and it grows. Then as t tends to infinity, it diminishes, and thus we have the steady state. So what I want us to do is just to have certain definitions that will be very, very helpful in order to understand this, and also will be very, very helpful when we'll be carrying out calculation. The first definition that we need to know is what we call the overshoot. Overshoot. So when you talk about the overshoot, then this is the maximum difference between the transient and steady state response for a unit step input. So we are simply saying that it is the maximum difference. It's the maximum difference between steady state and transient response. It's the maximum difference. So that is where we have this one. We usually refer to it as the first overshoot. So that first overshoot, it should actually be the highest, and that is what we refer to as the overshoot. At times we usually refer to it as the maximum overshoot, and it is always a measure of relative stability, and it is often expressed in percentage of the final value. We usually express it in percentage of the final value, whereby we can always say that the percentage overshoot will be given by 100e raised to negative zeta pi all over root of 1 minus zeta squared. So that is now the percentage overshoot. That is now what we refer to as the percentage overshoot minus zeta pi. So this one, all of these ones are raised to power e. So if you are not supposed to have it in percentage, then you will just say that it is e negative zeta pi divided by root of 1 minus zeta squared. So at times, some people may express it as a unit, while others may want it to be expressed as a percentage. So the 100 multiplication by 100 there caters for percentage. So in most cases, we usually talk about the percentage overshoot. So that is what the percentage overshoot is. And at that particular point where we get the overshoot, we usually have the time that is taken to reach the first overshoot, which is referred to as the peak time, TP. We usually have peak time, which is TP, and this is just the time that is required, or the time taken to reach, the time taken for the response to reach the first overshoot. So this is actually the time taken for the response to reach the first overshoot, And TP is always given by, the TP that we are talking about here is always given by pi all over omega n root of 1 minus zeta squared. So that is what the TP is. Or from the first principles, what we discussed, the TP can still be given as pi all over. We know that omega n root of 1 of the minus zeta squared, we can still refer to it as omega d, where that is now the damped frequency. That is now what we refer to as the damped frequency. So that is the definition of the peak time, and also the definition of what we call the overshoot. So you can see that the peak time TP is actually at the first overshoot, which is always higher. That is what we talk about as the overshoot. The other thing that we can also talk about is the delay time. We can also talk about the delay time, TD. Delay time, TD. Can talk about the delay time, TD. So when you talk about the delay time, TD, this is the measure of speed of the response, and it is always that particular time that is required for a response to reach 50% of its final value. So that is where we have 50%, that is 0.5, 50% of the final value, and that is where we have the TD. So the time that is taken for the response to reach 50% is what we refer to as the TD, or the delay time. And as we have said, it is always a measure of speed of response, and we've just said that it is the time that is required for a response to reach 50%. So basically we're saying that time required for a response to reach 50% of its final value. The time required for a response to reach 50% of its final value. So that is what we refer to as the delay time. Another important definition that we also need to understand is what we call the rise time, that is the TR. The rise time, that is the TR. So we can talk about rise time, which is what we call the TR. So from this, the particular rise time that we are talking about is actually the time that it takes for the response to rise from 10% or 0.1 or to 0.1 to 0.9. That is between 10% and 90% of the final value. So it is the time taken for the response to rise from 10% to 90% of its final value. That is what we shall refer to as the rise time. So we can say that this is the time taken for the response to rise from 10% to 90% of its final value. In other cases, it can still be described as the time taken for the response to rise from 5% to 95% of its final value, or we can still say that it is the time taken for the response to rise from 0 to 100%. So all those definitions can be used. But now, in the most commonly used is where you talk about the 10% to 90% of the final value. So that is what is commonly used. But even if you use the other one of 5 to 9% of the final value, or 0 to 100% of the final value, all these are always allowed. So that is the definition of what we refer to as the TS, that is the rise time. And the rise time in this case, the TR, I mean not TS, TR, and the rise time in this case, TR, is always given by pi. So TR in this case, so TR is always given by pi minus theta over omega n, or we can say pi minus theta over omega d, which is the same as pi minus theta all over omega n root of 1 minus zeta squared, where zeta is actually the damping factor. So that is what the rise time is about, and we can say that where theta, can say where theta, you can talk about where theta you can say where theta is actually tan inverse, where theta is actually the tan inverse. It is the tan inverse of 1 minus zeta squared root of 1 minus zeta squared all over root of 1 minus zeta squared all over zeta, and this one should be in 1 minus root of 1 minus zeta squared all over zeta, and this one should be in radians. So that is the expression for the theta that we talked about in that case. So that is now how we can get that particular value. Then the next definition that we can also look at is what we usually refer to as the settling time TS. Settling time TS. We can talk about settling time TS. So when you talk about the settling time TS, then we are simply referring to the time that is required for a response to reach and remain or maintain within a specified percentage of its final value. So that is where we have this. As long as it has reached a certain percentage, which is always plus or minus 2% to plus or minus 5% of the final value, then that is where we usually talk about what we refer to as the settling time. So at t tends to infinity, then that particular system will settle so that it reaches the steady state. So we are simply saying that the settling time is actually the time that is required for the response to reach and remain or maintain within a specified percentage or a specific percentage of the final value. Or you can still say that it is within a specified tolerance band, and this is usually between plus or minus 2% to plus or minus 5%. And you'll also find that this particular response usually stay within plus or minus 1% of its final value approximately in 5 J seconds. It usually stays approximately in 5 J seconds. It stays within plus or minus 1% of its final value within what we call 5 J seconds, where J represents what we refer to as the time constant. And therefore, we can say that the settling time TS, the settling time TS is always given as log, as negative of time constant zeta omega n, negative of zeta omega n log to base e, negative of zeta omega n log to base e into bracket p root of 1 minus zeta squared, root of 1 minus zeta squared all over 100. And that is now what we have as far as that is concerned. So that is how we can get the settling time. So that is how we can get the settling time when needed. The next thing that we can look at, and this one we had looked at earlier, but I don't think whether there is a problem in repeating. So we are talking about the time constant. We are talking about the time constant. So when you talk about the time constant is always the measure of the rate of the decay of the response. So the next one we can talk about time constant, which we are simply referring to as the measure of the rate of the decay of the response. This is the measure of rate of the decay of the response. The measure of the rate of the decay of the response, and this one is always given as 2J all over F, which is time constant is equals to 2J all over F, which is just the same as 1 all over zeta omega n. So that is what will always give us the time constant. So that is what will give us the time constant, where in some cases, the zeta omega n can as well be referred to as the damping factor. So we can always refer to it as the damping factor. So what we are going to look at next is some of the equations as far as the calculations on the differential equations are concerned. So that is all that we can talk about as far as the response of a second order underdamped system to a unit response is concerned. So we have a equation, second order has a differential equation of that, 1.5 d squared theta naught over dt, that one, all over that. So you are supposed to first of all determine the percentage overshoot, and then secondly you are supposed to find the time taken to reach this particular overshoot that we are talking about. So in that case, if you have such like The first thing that you are supposed to do is you are supposed to make this particular equation or this particular differential equation to look like what we refer to as the dimensionless equation, and then you compare the two. So the first thing that we are going to look at, for us to make it to look like that, we are going to divide that one by 1.5 so that this value here is made to be 1, which means we are going to divide all over by 1.5. So solution, divide the differential equation by 1.5. So in that case, we are going to have d squared theta naught all over dt squared plus, that is now going to be 2 d theta naught all over dt plus 4 theta naught is equals to 4 theta I. So that is now what we have. Then this is what we are supposed to now, we are supposed to look at it and compare it with the differential equation. We can compare only the first side, the left hand side. So we can say d squared theta naught all over dt squared plus 2 d theta naught all over dt plus 4 theta naught should be equivalent to d squared theta naught all over dt squared plus 2 zeta omega n d theta naught all over dt plus omega n squared theta naught. So this is now the dimensionless equation, and this is now the equation that we had before after transforming it so that that value resembles that value. So that is the reason why we were dividing, because this one had 1.5, but we wanted it to be unity. So we had that. So in that case now, we can now go ahead and find the values that we've been asked. We can now go ahead and find the values that we've been asked. So the first thing that we are going to look at is now we are going to compare the two equations and get the values of, we've been asked to get the percentage overshoot, and also we've been asked to get the time taken to reach the overshoot, which is simply TP. So from there we can still get the damping factor so that we can find. So comparing the two, we can say 2 d theta naught, so 2, therefore you can have the two equations. Omega n squared will be equals to 4. So this is omega n, so that is, ukiangalia theta, if you look at this, then you are talking about theta, so 2z, that is omega n squared is equals to 4, therefore omega n is equals to root of 4, which is simply 2 rads per second. 2 rads per second. Then after that, we can now look at, we now have the omega n, and therefore we can now compare the second part of that, that is 2 zeta omega n, with that, so that we can see that. So this one can be the first equation. So 2 zeta omega n should now be equal to 4. It should be equals to this 2. So we can say that that is equals to 2. But we know that the zeta, we know that omega n is actually 2. Therefore, we can say 2 times zeta times 2 should be equals to 2. Therefore, 4 zeta is equals to 2. Therefore, zeta is actually equals to 2 all over 4, which is equals to 0.5. And because that is always a ratio, ratios don't usually have units. So it is simply 0.5. But remember, we have not even answered one of the questions because we have been asked to get the percentage overshoot and also the time taken to reach the overshoot. But these values are very, very important. The value of omega n and the value of zeta will be very, very key in finding those particular values. And therefore, we can now get the percentage overshoot. Percentage overshoot, that is now the first one. The percentage overshoot is equals to 100 e negative zeta pi all over root of 1 minus zeta squared, which is simply 100 e negative, what is our zeta? Our zeta is 5, negative 0.5 pi divided by root of 1 minus the value of zeta is 0.5. So 0.5 squared. So that is what we are supposed to evaluate. And if we evaluate that, then we are going to get that value. So this is going to be like, we are going to have the value there to be around, if you do it, then we are going to get, this is equals to 16.3%. So that is now what we have. So we can still reduce that because it's going to be 0.5 pi divided by root of 0.75. That is 1 minus 0.25 root of 0.75. So that we multiply that, we get the, we divide that, then we multiply that one by e, then that one will be raised to power e, then multiplied by 100. If you do that, then you are going to get the value of the overshoot to be 16.3%. So with that, you shall have answered the first question. So we can look at the second question, which is now the time that is taken to reach the overshoot. Time taken to reach the overshoot, that is the second one. So the second one, we are talking about TP, and we remember the value of the TP, we say that TP is given by pi over WD. So TP is given by pi all over omega d, which is the same as pi all over omega n root of 1 minus zeta squared, which is now going to be pi all over omega n. We found it to be 2, so we have 2 there. 2 root of 1 minus zeta squared. Zeta is 0.5 squared. And if you do that, then you'll find that this is going to be, because this is now an element of time, then this is now going to be what we can talk about as 1.814 seconds. If you do it properly, you'll get 1.814 seconds. And that is now the solution to that particular question. So that is now the equation that I want us to look at. A second order system is represented by the differential equation. That is the differential equation that we're talking about. 2d squared theta naught over dt squared plus 9.6 d theta naught over dt plus 144 theta naught is equals to 144 theta I. Then the equations are there. You are supposed to determine the output response of the system, the percentage overshoot, the time taken to reach the overshoot, settling time, and also the time constant. So those ones are what we are supposed to look at. So the first thing, even without looking at what you are supposed to get, you are supposed to compare this particular differential equation that you have been given to the dimensionless equation. And for you to compare it with the dimensionless equation again, you have to ensure that this part here, the 2 here, is everything is divided by 2, so that the highest order, that is the second order or part of that particular differential equation, is unity. That is when you can compare it with the differential equation. So in that case, we can say the solution here, dividing by 2, we divide by 2 to make that one to be unity, and then it means that we'll be dividing all over by 2. Therefore, if we divide by 2, we'll have d squared theta naught all over dt squared plus 4.8 divided by 2. It's now be 4.8 d theta naught all over dt plus 72 theta naught is equal to 72 theta I. Then from there now, we can now compare this one with the dimensionless equation. So you say comparing the equation with the dimensionless equation, with the dimensionless equation. So if we compare this equation with the dimensionless equation, what are we going to get? So you are supposed to compare this one by the dimensionless equation. The dimensionless equation here is going to be d squared. So it means that we are going to talk about d squared theta naught all over dt squared plus 4.8 d theta naught all over dt plus 72 theta naught. Then that one you are supposed to compare with d squared theta naught all over dt squared plus 2 zeta omega n d theta naught all over dt plus omega n squared theta naught. So that is what you are supposed to compare. So if you compare that, you'll have the two equations. Omega n squared will be equals to 72. Therefore, omega n is going to be root of 72, which is equals to, so the root of 72 here, we are going to get, if you get the root of 72, what we are going to get is the root of 72. This should be 8.49, and that one should be rads per second. So that one will give you omega n. So that is what is going to give you omega n. Then after getting omega n, it is also very crucial that you get the zeta, because all those values will be used in order to determine the value. So from there, we can use the second part, that is now 2 zeta omega n should be equals to 4.8, which means zeta, which means omega n we know. So we have 2, so zeta will actually be equals to 4.8 divided by 2 times 8.49, which is now going to give us. So if you do that, do that, what are we going to get in that case? So we are going to get the value of zeta to be, our value of zeta will actually be 0.28. So this is going to be 0.28. So that is the value of zeta. So after we've gotten the value of zeta, then we are now going back to look at what is the equation of a second order underdamped system, because actually from what we have here, we said that when the value of zeta is actually less than 1, then we can talk about an underdamped system. So the equation that we are going to use is the response that for the underdamped system, which is always given by theta naught is equals to theta I into 1 minus E negative zeta omega nt all over root of 1 minus zeta squared sine into bracket omega nt root of 1 minus zeta squared then plus phi. So that is now, then we can now close the bigger bracket. So this is what we are going to find the values that we can get and slot inside there in order to give us the response of the system. So in that case, we can say that we don't have theta naught. So theta naught is going to be given by theta I into 1 minus E raised to power negative zeta. So what is negative? 0.28 times omega n 8.49 t, 8.49 t. Then the whole of this one should be over 1 over root of 1 minus 0.28 squared sine into omega n 8.49 t root of 1 minus 0.28 squared then plus phi, of which the value of phi, we can also obtain the value of phi very, very fast. We are able to obtain the value of phi. So that is now the expression. So when you talk about the value of phi, the tan phi, but tan phi, we can say tan phi will be given by, root of 1 minus zeta squared, root of 1 minus zeta squared all over zeta, which if we evaluate, we are going to find root of 1 minus 0.28 squared all over zeta, which is 0.28, and therefore that one, if you evaluate it using the calculator, you are going to find that theta is equals to 78. If you get the tan inverse of what you are going to get, then you find that theta is actually equals to, theta will be equals to 73.74 degrees. So that is the value of zeta. So that is now what we can have in that case. So after that, we will go ahead and simplify that one further so that we can get the expression. We can simplify the expression further. So maybe we can simplify the expression further. We can simplify this particular expression further, whereby we can say that theta naught is now equals to theta I into 1 minus E, and this one should now be, if you simplify that, it will be E raised to negative 2.38t, and this one should be divided by 0.96 sine. So if you do that, so you multiply by that, then you simplify that, which is now going to be 1 minus 0. That, then if you get its root, then you find that it is 0.96. Then from there, you have the sine into 8.15t, 8.15t plus 73.74 degrees. So that is now what we are going to have in that case. So this is now, if we evaluate, if you simplify both parts. So because that multiplying by that is now what brings us 8.15t. So that is now the expression that you are going to have. You can simply get the reciprocal of that to simplify that one further, so that you can say that theta naught is equals to theta I into 1 minus, we can get the reciprocal of that and multiply by that, and therefore if we do that, it is going to be 1.042 E negative 2.38t sine into 8.15 t plus 73.74 degrees, and therefore that is now the expression for the output response. That is now the expression for the output response. So in that case, we shall have answered the first part of the equation. So now we can go to the second part. The second part, we were asked about the percentage overshoot. So we were supposed to get the percentage overshoot. And from there, the percentage overshoot, we have said that it is 100 E negative zeta pi all over root of 1 minus zeta squared, which is now going to be 100 E raised to power negative zeta, negative theta. Theta will be negative theta pi, not theta but zeta. So we have negative 0.28 pi divided by root of 1 minus zeta squared. 1 minus zeta squared, which is now going to be again 1 minus 0.28 squared, of which if we evaluate this, then it will be 39.999, which is approximately 40%. So that is going to be 40%, and that is now the percentage overshoot. Then after getting the percentage overshoot, which is the second part of the equation of what we were asked, we can now go ahead and get what we refer to as the TP, which is the time taken to reach the overshoot, the peak time, TP, and TP is actually given by pi all over omega n root of 1 minus zeta squared, which is simply going to be pi all over omega n. We found it to be 8.49 root of 1 minus 0.28 squared. So that is now what we are going to have That is now what we are going to have and evaluate it. And if we evaluate it further, we are going to get 0.39 seconds. Then that is now the third part of that equation. Then the next thing that we're supposed to get is now actually the settling time. So we are supposed to get the settling time. So, and we know from what we talked about as far as the settling time is concerned. So the settling time here we can talk about the settling time Ts, and we did say that Ts is given by minus 1 all over zeta omega n, and this one we are supposed to have log to base e, p, log to base e, p root of 1 minus zeta squared all over 100. So this is what we are going to have, which is going to be negative 1 all over, the value of zeta is 0.28 times omega n. Omega n is 8.49 log to base e into p, and the value of p, we were told to take p to be 2. So 2 root of 1 minus 0.28 squared all over 100. So this is what we are supposed to evaluate. So we are supposed to get the whole of this value, then get its natural log. Then we multiply by the value that we have here. So if we do that, then this is going to be what, if we evaluate all this, so getting all that and that, then multiply them together. So this one, we are going to evaluate it separately, get the natural log of that value. Then that one, we are also going to evaluate it separately. So if we evaluate this, then this one is going to be minus 0.42. And this one is actually the time constant. And the next question that we are going to be asked is the time constant. Then you multiply that one by the natural log, which is minus 3.925. And if you do that, if we evaluate that, then we are going to find the value of this to be 1.66 seconds. And that is now what we refer to as the peak time, or the TP. Then after that, we can now go ahead and look at the time constant. Time constant, of which we have seen what it is here, just above there. So the time constant is given by 1 all over zeta omega n, which is simply that from there. So you can see that, which is simply 1 all over 0.28 times 8.49, which is equals to 0.42 seconds. And with that, you shall have solved what all that particular equation wanted, all that was needed in that case. So that is now what we can do as far as that is concerned.